last talk of this workshop, before we start the discussion, will be given by Rolfe. Rolfe is a research engineer at Signal, working on bringing security into production. And the last session you've already heard about some of his work, but today he will tell us more about the post-quantum ratcheting for Signal, with a focus on the actual candidate protocol Signal just released.
All right. Oh, yeah, thank you very much. I'm really happy to be here today. I'm Rolfe. I'm a research engineer at Signal. And happy to have the chance to talk about some of the work we've been doing over the last year designing a post-quantum ratcheting protocol. Now, first of all, it's not just us at Signal doing this. Like, we're all standing on the shoulders of giants here, right? And we couldn't do this without the work the original creators of Signal did and everybody who's built it into what it is today. And also the learning we've had from the community that have given us the intellectual tools to actually reason about the security and design of these protocols. But also, this wouldn't be possible without some really great collaboration. We have Benedict Graham is a fellow engineer at Signal, Danny Shu, Daniel Toma. Really, they shaped what we have today. So anyway, let's get started with it. Unsurprisingly, the starting point is a Signal protocol. I don't think after the last few talks I need to say too much about this, and to say it's widely considered to be a standard for secure messaging to parties. It's used by a lot of people. And very reasonably 10 years ago, when it was, more than 10 years ago now, when it was first designed, it was not designed to be post-quantum secure. Right. But things have changed, right? Not only is the quantum threat 10 years closer than it was, I can say that much with confidence, but also we've got much better tools to mitigate these risks today. So it's practical, and we want to do that at Signal. We want to stay well ahead of any of these threats. And ensure that in this post-quantum world, our user privacy is still going to be preserved. So, to see how to do that, we need to dig into the details of the protocol a little bit. We just heard a little bit about the protocol in a couple of earlier talks. At a high level, it consists of two parts. The first part is a handshake protocol, ECDH, that Philip just mentioned a little bit. It allows two parties to asynchronously agree on a shared secret that has post-quantum harvesting how to encrypt layer security. This secret is then fed into the Double Ratchet protocol, which provides encrypted communication with continuous key updates that provide some important security guarantees. And Leia did a nice job kind of breaking down exactly how this ratcheting works. It's got two parts. The symmetric ratchet is going to give us a forward secrecy. And the Diffie-Hellman, or public ratchet, gives us post-compromise security, or yield. When looking here, like, where are the threats, the quantum threats? There's certainly still one in PQXDH, right? PQXDH is not secure against active quantum attackers. And the sort of things Philip was just talking about are going to help make that practical. I'm looking forward to getting there. But looking at this, it's no real surprise where the problem is. The symmetric ratchet uses symmetric key crypto, it's fine. The Diffie-Hellman ratchet is what we're going to need to fix. So, basically, what are we doing? We need post-quantum, we need ECS, and we need a new public ratchet. So, let's talk a little bit about how we're going to build that. And to do that, it's good to start, well, what's the problem with what we have now? So let's look a little more carefully at the Diffie-Hellman ratchet. The Diffie-Hellman ratchet is something we call a continuous key agreement protocol, using the language of Alwyn Gray, Dotus 2019 here. And in particular, the CKA protocol, so continuous key agreement, or CKA, the one we're using at Signal today works like this, that we have two characters, Alex and Blake. Blake starts with some secret B0. Alex has the public part, G to the B0. And Alex wants to talk to Blake, so what does Alex do? Sample a new secret, A1. And compute a shared secret, K1, which is just G to the A1 B0. Now, of course, Alex knows that Blake knows B0, so they can send G to the A1 over to Blake, and Blake can compute K1 too. And so this means any other message that Alex wants to send to Blake, they can encrypt using K1. And they know that when Blake receives the message, they'll be able to compute K1 and carry on, process that. Now, Alex may have to repeat this a few times if Blake is not talkative. But eventually Blake responds. And what does Blake do? Exactly what you expect. Sample a new secret V1, compute a new shared secret K2, send the public key corresponding to V1 over to Alex. Alex computes K2, ratchet, ratchet, ratchet. One thing I want to point out though, right now we use curve 25519 in production. And for that, this G to the A1 is actually a curve point. It's 32 bytes. Doesn't seem like much, like, oh, 32 bytes, who cares? I'll point out that the minimal double ratchet message today is 66 bytes. This is over 2/3 of the messages we send. 32 bytes of that 66 bytes is here. So think of that as expensive, okay? Why do we almost double the size of our messages like this? Well, because we get post-compromise security. So what happens here if an attacker is able to infiltrate Alex's device and learn the secret A1? Well, pretty clearly they're going to be able to compute K1 and K2, just straightforward computations, but they didn't learn B1. They didn't learn A2. K3 is going to be indistinguishable from random to that adversary. And so will all of the keys that follow. So here they healed, right? This is nice. This is why we pay that price. That's our post-compromise security. Now we just want this in a post-quantum setting. Well, it turns out Alwyn, Coretti, and Dotis already did this for us. In their paper where they introduced the CKA abstraction, they also provided 4 instantiations. And one of them can use a standard KEM just like ML-KEM. And really, it's structurally the same sort of thing. You know, Blake's still starting with a secret. What is the secret now? The secret is a decapsulation key. Alex starts with the public part of that, the corresponding encapsulation key. So Blake has EK0, Alex has EK0. What does Alex do? The first thing is you sample a new secret. Now that means sampling a new key pair, EK1, DK1. And you create a new shared secret. Now that means encapsulating shared secret to EK0. Now Alex has to send EK1 and CT0 over. Blake receives it. Blake can save EK1 for later, immediately decapsulate the ciphertext, get the shared secret, and go on. When it's Blake's turn to send, we do the same thing, and we ratchet, ratchet, ratchet. Everything's good, right? This gives us our post-quantum ECS. But remember when I was complaining about that 32 bytes before. Now, let's say we're using ML-KEM 768. I mean, it's no surprise this is big, right? So that's going to be 2,272 bytes. So we're in a situation now where this, minimal double ratchet message I was talking about, which is the majority of our traffic, we just multiplied the size of that by 35. That's expensive. That's expensive for us. That's expensive for our users. And it also is going to cause usability problems for users in low bandwidth settings. So this isn't something that we can deploy. But it's still a good idea. We want to do something with it. So what are we going to do? We have to figure out how to work with bandwidth limits. Now there's basically 2 approaches here I can think of. One is what Apple does in PQ3, which is amortize the cost, don't send anything for a long time, then send a big message. Unfortunately, to get immediate decryption, they have to keep sending that message for a while. There's settings where I think that's a great thing to do. There's settings where it's a challenge. And we're facing some of those settings, so we do the only other thing you can do is like take a big message and break it into smaller chunks and send one small chunk with each message. Well, yeah, but we also have to make sure that this works, even if these messages can be maliciously reordered or dropped. So we can't just say, oh, okay, I got 30 chunks, I'll send them to you, I hope you got it. I can't do round robin, have to do something more sophisticated. Well, so fortunately there's a primitive that pretty much does exactly what we want, which is called an erasure code. Fountain codes are similar, subtly different, but they do the job as well. All this does is, okay, I've got a big message I want to send, I can feed it into an encoder, and it's going to give me a stream of code words, indefinitely long. The important things about the code words are they are fixed size, smaller than the initial message. Depending on how long the message is, we'll say the first 10 code words concatenated together give us the original message. We're not talking about a systematic erasure code. That concatenation bit is a systematic thing. There's some details. The code words actually need a little metadata in them, so it's not exactly like that. But you can think of, kind of break the message into chunks like this. But the thing is, we can go past n. We can just keep streaming code words. And now, this is the erasure code part of it. We can tolerate erasures in the stream of code words. So as long as any n code words make it to the recipient, they can feed it into the decoder and reconstruct the message. The difference between erasure codes and fountain codes is fountain codes, it's probabilistic, but they're also faster. So you choose. Okay. Good, so with this primitive, we can do what we want. We take the protocol I showed you before, and Alex needs to send EK1CT0. So what do? Use the erasure code, break it into chunks, start streaming the chunks over to Blake. Now Alex and Blake are still talking, and so Blake is like sending a bunch of useless messages back as far as this protocol is concerned. But they go on, eventually it gets through, they swap roles, and now Alex is sending useless stuff, and so on. But yeah, this works. Like, this is a protocol. There's some subtleties we have to change. Like, you'll notice all these back and forths, most of the time they're not emitting new keys. We're back in that CKA world. Every send and every receive would emit a new key. So syntactically, this does not fit the CKA abstraction. So we made a kind of natural modification to CKA to create something we call a sparse CKA. Because we changed the syntax, the secure messaging constructions based on CKAs didn't work exactly, so we need to modify those, but we have a secure messaging construction based on sparse CKA. And so we can put all this together, and we have a provably secure ratcheting protocol that seems to check all our boxes, right? So we're done, it seems. Just take ML-KEM from ACD19, use our chunking compiler to turn it into a sparse continuous key agreement protocol, use our secure messaging construction built on top of any sparse CKA, and we have secure messaging with module learning with errors security. We'll talk about hybridization later. We do want hybrids. We're not saying everybody should hybridize, but we will this. So there we go. End of story, right? Well, no. I don't know how many times over the last year I thought we were done. But you do the best you can until you know you can do better. And what do you do when you know you can do better? Yeah, we're not going to ship something if we know we can do better. So we need to do better. So how can we improve these SCKA protocols? I want to kind of emphasize the pain in the protocol I just showed you. Blake is sitting there twiddling their thumbs, and that should bother you. But also, let's look at the attack surface. So I'm coloring the shared secrets these users have to store in yellow, and the decapsulation secrets in orange, and trying to emphasize their lifetime here. And so while Alex is sending this message to Blake, they have to hold on to the shared secret that they encapsulated. They have to hold on to that decapsulation key until they get a response back to Blake. And meanwhile, Blake has to hold on to the decapsulation key corresponding to CT0. Then they're going to flip, and everything's kind of mirror image, so on and so forth. This takes a long time to spit out keys. Parties are doing nothing when it feels like they should be doing something. And the attack surface is huge. So, what can we do? Well, there's some ways, unfortunately, they're in tension with each other, but ways we can do better. One of them is, maybe we can just reduce that attack surface. Another is, well, we're blocked, you're twiddling your thumbs, we'll do something. I mean, what can you do? Sample a new key pair, start sending that. Right? But last, and maybe in the end, most importantly, maybe KEM is not exactly the right abstraction for building a ratcheting protocol. And if we open up the KEM black box and look at the internal structure, there's some better things we can do. So let's make some of this concrete. Just like, how might we be able to reduce the attack surface? I hope some of you felt like almost physical pain looking at that protocol, because if you had any empathy for Alex and Blake, Alex is there, Alex knows Blake is holding DK0, and if Alex could just get CT0 over to him, then they could use it, they could ratchet, delete, and move on. Why on earth would Alex sample a new key pair right now? No, so Alex just sends CT0. Send CT0, Blake's got to send an acknowledgement that, hey, I got it. Then they can ratchet to that. Now Alex samples. And so on and so forth. Still the same amount of thumb twiddling. We didn't do anything about that. We don't spit out keys any faster. The first one came out faster, but on average, there's no change. but the attack surface looks a lot better. Like the lifetime of every secret we're storing is shorter. There's periods of time where some parties have no secrets related to this protocol, and we never double up. So that's good. That's progress. But can we quantify the progress? We'll talk about that in a little bit. But that seems like unambiguously better. Another thing we could do is sample early. In this case, well, Blake says, well, I'm going to do something. I'm going to sample another key pair and send it too. This gets interesting if one party's sending a lot faster than the other. You're like, well, do you sample 3 key pairs ahead, 4 key pairs ahead? You know, it could be a disaster. But you go through and, you know, here we're spitting out, it's a little funny, they're spitting out keys at about the same time in balanced communication. But you spit out keys twice as fast. You ratchet faster, that seems good. But you also increase the attack surface a bit here. Unclear, is it twice as good? Hard to say. But it is a tool in our toolkit to use. Okay, so the next thing I want to talk about, there's a couple of ways to do this. But what happens if we look inside our KEM? So let's look at the structure of an ML-KEM encapsulation key in ciphertext. The encapsulation key, we'll use ML-KEM 768 for reference. The encapsulation key is 32 bytes, and the rest of it is what I'll call a noisy vector. It is 1,152 bytes. The ciphertext consists of 2 parts. There's a compressed noisy vector, which is kind of like structurally almost the same thing as the noisy vector in the encapsulation key, and a reconciliation message, CT1 and CT2. The important thing about this, though, is that to compute CT1, all you need is this C from the public key, 32 bytes. And because of the particular FO transform they use, we also need hash of the full encapsulation key. So this is 64 bytes total that we need to compute this. To compute the rest of the ciphertext, of course, you need the entire encapsulation key, or we wouldn't send the entire encapsulation key. Right. So this allows us to have an incremental interface to ML-KEM, where instead of a single encapsulation function, we now have encaps1, which computes this CT1 for us and gives us a secret we have to hold for later. And then encaps2 takes that secret, takes the rest of the encapsulation key, and produces CT2. And that opens up a new possibility. You know, instead of like sampling an entire new key pair and sending the encapsulation key early, if somehow we can get Blake enough information to sample CT1, that's another option. You could sample CT1 and start sending that. Okay. I want to say, though, there's other things we can do with these KEMs. So please, in a couple of days at Eurocrypt, check out our talk. Daniel Yost will be giving that. About ratcheting KEMs. So there the observation is, yeah, these EK and CT1 are more than just coincidentally similar. That in fact, you can use an EK as a CT1 in your next round of communication and significantly reduce the communication costs. This is a pretty interesting notion that I think I'm really optimistic about for the future. But right now we'll be talking about improvements. So, where are we? We have some ways to improve our protocols. So the design space is huge. We have to decide what kind of KEM we're using. We have to decide when are we going to sample a new key pair, when are we going to sample a new ciphertext. If we have a choice about what to send, what do we prioritize, and so on. So, let's see, I think I lost the... there we go. Oh, let's see. Okay. The other big question, and this is a tough one, is how do you choose? You know, I have one option that generates keys faster, another option that has a small attack surface. Which one is better? Well, at the end of the day at Signal, what we care about is, in an attack, how many users' messages get leaked? Like, we call this the vulnerable message set, the set of messages that get leaked to get exposed in an attack. And we want that to be as small as possible. That's the only reason we care about a small attack surface. That's the only reason we care about ratcheting fast, because we want confidentiality. The problem with this is that the vulnerable message set depends completely on messaging behavior, right? So we have to get into the business of modeling realistic messaging behaviors, running statistical simulations, comparing distributions. And so this is an entire different talk. I hope we'll be able to share a lot more about details about this in the future. But needless to say, we actually implemented over a dozen protocols. We ran a big suite of statistical simulations comparing the distributions. Through that process, there's two protocols that stood out as particularly robust. One of them was an opportunistic version of Katana, which is our Ratcheting KEM. We'll be talking about a Eurocrypt. And the other is an opportunistic version of the incremental KEM. And this is the one we chose. We're calling it the ML-KEM Braid protocol. And this is our sparse continuous key agreement that we're going to build secure messaging from. So the main idea here is pretty simple. Remember I said you could compute CT1 if you knew the seed and a hash of EK? Well, just send those first in a header message, right? So now the protocol looks like this. Alex samples a key pair and starts sending the header. It's only 64 bytes now, so there's some fooling going on, but not too much. When it gets that, they can sample CT1, start sending it. The first chunk of CT1 that Alex gets, boom, they can say, hey, I don't need to send the header anymore. Just start sending the EK. EK's a little bit longer, so maybe Blake has to wait a bit. Finally send CT2, send an acknowledgement. We can all ratchet, move on, change directions. That's the protocol. Okay, well in reality there's a lot of edge cases. You know, Alex might send faster than Blake and so on. We have to make sure we cover all the corners. So we do what engineers would do and say, okay, well, let's make this a state machine and prove that we covered all the cases. And then we're going to specify it that way. We write our code that way. We can reason about the code locally. And very nicely also, it's easy to translate this into tools like ProVerif so we can perform formal verification. And with this, you don't need tools like that, though. I mean, it's tedious, but you know, if I had given you the full spec, you can see that Alex and Blake, when you start them in the right states here, are not going to come anywhere close to exploring the full product state space. There's a very narrow path of states they can go through. And importantly, each one of these states, they will be able to make forward progress. One of them will be generating messages that will move the other out of the state they're currently in. So, with that, let's say arbitrarily, because 42 is a good number, we say, and it's close to like the 34 bytes we do for the classic Double Ratchet today. If we allow a 42 byte per message overhead, then this turns into a 1.6-fold increase in our per message cost for that standard small message. This is still significant, like this is a real cost. This is most of our message traffic. But it's consistent and reasonable, something we can definitely live with. The trade-off is we have to ratchet a lot more slowly. If we up that limit, of course, we can go faster. So putting it all together, we want to integrate this with classic ratchet. We want hybrid security. Don't need to say too much about this. Basically, what I want to say is, if you think of both of our secure messaging protocols as these black boxes that are going to spit out message keys that we can use for encryption, then to get hybrid security, just take the post-quantum message key, take the message key from our classic Double Ratchet, KDF them together, get a hybrid secure key, right? The beautiful thing about this is like, we almost don't have to touch our current implementation, right? So we can change one thing at a time. The things we'd like to change in our current implementation, yes, let's get there. Okay. This isn't just theory, this is real. We've been building it. We've built, I don't know how many versions of the protocol, but we've settled on this. We started from the beginning working with Crispin to integrate formal verification into the process. They helped us settle on modular construction of the protocol so that we could verify components independently. We built ProVerif models from the start of earlier versions of the protocol, so that as we kept finding places we could do better, like we at Signal could quickly tell, we didn't have to go back to Crispin to ask for a new model. We could just go ahead and tweak the model and find out if it worked. And sometimes we found, oh, it didn't work. We have to fix some things, right? So we used ProVerif as part of the design process. And I believe it helped speed our arrival at high quality designs. They also helped us put Hack's formal verification tool into our CI pipeline. And generally kind of gave us guidance on writing proof-friendly Rust code. There's not too many restrictions though. So now we have a formally verified implementation. We proved that it's panic-free, which may not sound like a big deal, but we have security-relevant asserts aggressively placed throughout the code, and we proved that they do not fire. We also proved the correctness of our GAW field arithmetic that we use for implementing the erasure codes. And we have programmed models of the ML-KEM Braid and of our symmetric ratchet. The big thing I want to point out here, though, is that the formal verification now is like a dynamic part of our engineering process. This is not something that throws our implementation. Every time our engineers push code, we extract from the Rust code F-star models and prove that they are safe. Right? Prove that they are correct. And if they fail, the build fails and we fix it as an engineering problem. Yeah, there's code. So public, I think, as of 2 days ago on GitHub. So not deployed yet. We're getting there, but definitely welcome all the eyes on it we can get. We love scrutiny and feedback. Yeah, and I think this it's not the end of the story. I was talking about ratcheting KEMs. There's certainly a lot more work to do. Questions I have about this vulnerable message set and how to model message behavior. All sorts of work. But I'm really happy to say that I think we're making real progress and we're close to being able to deploy this and increase the security of our users. So that's it. Yeah, happy to take any questions and feel free to contact me, email, signal, whatever. So.
Do we have any questions in the room? Okay, then maybe I have. You said that the KEM abstraction didn't match. Can you be a bit more specific about what the mismatch between the KEM interface and the ratcheting protocol is?
Yeah, so the double ratchet, the classical double ratchet is really like a Nike that we're using, right? You're doing a key exchange. And when you look at what's working, like what did we do with the incremental KEM, or when you look at the ratcheting KEM, we'll talk about a Eurocrypt, you're looking at the lattice-based KEM as almost a Nike. You come to this like noisy key agreement, but then you have to send a reconciliation message. But the bulk of the work is with that getting almost there to a key agreement. And that seems like closer to a good, so I'm not sure like what the right thing is, but this is just like a feel for what we're seeing in the process.
Okay.
Yeah.
Yep.
I was wondering, thank you for the talk. Since you use the word reconciliation in particular, and since you're splitting Kyber or ML-KEM into two different components, so technically they're not ML-KEM anymore, I'm guessing. Are you afraid at all about patterns?
So no, that is a question. Certainly when it comes to like adopting more aggressive optimizations. For example, I'd love to get rid of that header. Like if we didn't need to use that FO transform, obviously the parties, they already have shared state. They could agree on a C without saying that, right? So that would make it better. So we are concerned. That's the only reason the header's there, to try to stay, bitwise on label with ML-KEM. Now we're not using the ML-KEM interface, and I'm not an IP expert here, right? Bitwise, we're still using ML-KEM as specified, and we would like to be able to move away from that, for sure. But yeah, our expectation is that this is okay. Now that's a good question, and it is top of mind for us. So.
Any more questions?
Sure. I guess all this is a very big departure from the like minimal modification model, like for instance of PQ XDH. So it's a very big step. So do you think it's how would you weight like post-quantum forward secrecy and post-compromise security over the scale, like together with your impression of how far quantum computing, big quantum computers actually are?
Yeah, so I would say, PQXDH was an obvious step to take because it was such a small change to the existing protocol, and so relatively lightweight, and the benefits are huge, right? In terms of we're protecting our users today from a potential threat in the future, a complete loss of privacy in the future. The benefit of this is quite a bit more marginal. I would say in terms of PCS, it requires a much stronger attack for this to become relevant. But at the same time, eventually we want to move to fully hybrid security. We don't want to throw away the elliptic curve-based guarantees until we feel like they're not meaningful anymore. You know, this is an important step towards getting there. And there's another benefit of hybrid security is, you know, what happens if there's advances in elliptic curve cryptanalysis? So we need to move to a bigger curve. That's fine, we can do that, but this is going to give us some, like, make it not a fire drill, right?
Yeah.
And so that's one of the big things I like from this.
Okay. Then let's thank our speaker again.